Okay, thank you, Pavel. This is your second installment for Monte Carlo. And in this one, we're going to do matrix elements and parton showers. So if you remember from the last lecture for Monte Carlo event generators, we kind of had a number of different steps. The first step being some sort of hard process. The second step being some sort of parton shower. And then some sort of third step here where we have hadronization, and a final step where we have decays and things like this. So this is going to cover that part of matrix elements and parton showers. And the reason that these two are grouped together is because both of these can be calculated perturbatively in QFT. And so that's why we do these two things together. Okay, so So in terms of where we're going after this, the next lecture, which will be on Monday, we're going to cover the non-perturbative components. So specifically multi-parton interactions, although we still use a perturbative framework to do that in Pythia at least. We'll talk about that, but it is really kind of a non-perturbative effect. And then hadronization, and then other non-perturbative effects as well, which we'll cover in that next lecture. So today is all about the perturbative side, and then the next lecture is all about the stuff that's not perturbative. Okay, so this is something that, let me get rid of this down here. Oh, it just did it, well, automatically. Okay. Hide video panel. All right, well. Okay, so this is hopefully a formula that you've seen quite a bit now and that you're really familiar with, which is just that we have this factorization theorem. So we have our two PDFs, and then we have our partonic cross-section sitting right here. So if we want to calculate a cross-section at the LHC, we need to know the PDFs for the protons, but we also need to be able to calculate out this partonic cross-section right here. So we don't need to dwell on this too much, but we know that, let me get back to this again. We know that this works for some processes, and it's assumed for many. And this parton function distribution, distribution function, it really depends on the flavor of the parton. It depends also on the longitudinal momentum fraction for this parton. It depends upon the factorization scale. And then we also have this partonic cross-section here. So this factorization scale, right, this is the scale at which this partonic cross-section typically is being calculated that we put into this factorization right here. So to be able to generate these events, what we need to be able to do is we need to be able to sample phase space somehow according to this differential cross-section. So specifically, if we have this cross-section differential in whatever type of scattering process that we have, we need to be able to sample it accordingly so that we can then say, let's say 2 quarks coming in, 2 quarks coming out. We need to be able to generate what the distribution for those 2 quarks coming out looks like. And in principle, this sounds really quite simple. In practice, implementing it is a little bit harder. So to do it, we need the MC techniques that we had from lecture 1. Specifically, we need to be able to do this type of sampling that we had. And on top of that, we really need to think really for a long time about the type of kinematics that we have to make sure that this type of sampling is something that's tractable and fast. Okay, so something else that I want to point out here is that this is just a little cartoon of PDFs here, right, where we have, for example, the up quark, the down quark, the gluon, and then the C, and this is at a relatively low Q. Something that's really important in event generators like this is that you oftentimes need to be very careful about the type of PDF that you're using, particularly when we get to the parton showers. But for the case of PDF generators, you want to make sure typically that you match the order of your PDF with the order of the matrix element that you're using. Now, that's not always the case because you can have a PDF that basically will incorporate higher order effects that you can use for a leading order matrix element. But for the case of parton showers where you truly need a probabilistic interpretation of the PDF, then you need to use your leading order PDFs. Okay, so that's just a brief aside, but it's something to keep in mind. Okay, so back to the issue at hand, which is how do we sample these kinematics? Well, these are diagrams that I think you're all familiar with, which is that if we have a 2-to-2 scattering process, we can define it in terms of these Mandelstam variables, right? So we can have something like S channel here, where we have P1, P2, and then P3 and P4. Then we can have something like T channel, where we have, again, this type of diagram, but now we have these lines stretching across, and you can think of these as fermion lines or whatever the process might be. And then finally, we have the U channel where we have these things swapped. So we have these 3 different types of channels for this standard 2-to-2 sampling that we need to do. Now, of course, if you're going to higher orders, so if you're going something like 2 to 3, 2 to 4, something like that, this type of factorization for the kinematics no longer works, but it's a very illustrative example to look at the 2 to 2 case first before you go to higher levels. Okay, so these are the types of kind of kinematics that we can have, S, T, or U, for a scattering process. So then how do we go about constructing this? Well, the first thing that we do is that we define the forward momentum of the two beams. And for the case of the LHC or whatever type of accelerator we're working with, in event generators, we typically like to define them so that they're right along the z-axis. So that means that I can give my first beam as P1. My z is just my energy fraction, or my energy times my x1. So this is my momentum fraction that I have. And I can do the same thing for P2 as well. And in this case, I'm assuming that we don't really have to worry about mass at all, which typically is the case, although it can be accounted for. But here, it's simpler to write it as this, so it's more clear. So then what we can do is we can write out what S hat is. We can write it out in terms of x1 and x2. So we take our center of mass energy S, we multiply it by x1, we multiply it by x2, and this gives us S hat. And S hat is S for the partonic cross-section specifically. And that's what we're interested in when we're sampling this matrix element, is that we need to know what scale this thing is at. So not in terms of the beams themselves, but rather from the actual partonic interaction that we're looking at. Okay, so now that we have that, how do we go about and actually distribute what our particles look like? So what we do is we look at this for something like the LHC where we have unpolarized beams. Then that means that our azimuthal angle, so our angle here in this transverse plane, that we only care, that we don't care about it because it's going to be uniform. And this is actually really important in Monte Carlo generators. When we have two beams coming along the z-axis and we're looking at the transverse plane and they're unpolarized beams, then we end up with this uniform distribution along that angle. And that's very useful because we have random number generators where we can just sample a phi, no problem. So what we do care about here then is theta hat, and this is going to be in the partonic frame that we're talking about here. So theta that we're sampling for this partonic cross-section. So what we can do is we can write out these relations. So we can write the sum of these Mandelstam variables. And from that, then we can work out what T hat is and what U hat is in terms of our angle of cosine theta hat. And so we can do that as follows here. And so what we can do is, if we know our S hat, we can then calculate our T hat, assuming that we sampled a theta hat. And so what that means is that we can then sample our theta hat here. Okay, so that means that the things that we want to look at for this type of sampling is that we need to consider x1, x2, and cosine of theta hat. Those are the three variables that we're interested in. If we know what these are, then we've defined the system fully. And the nice thing about that means that we can then somehow try to figure out how to sample this theta hat. Okay, now it turns out that while these are the things that we need to know, and these are probably in terms of the way that we typically integrate these cross sections or these matrix elements, it turns out that there are other variables that are more useful to actually sample from because they're better behaved in terms of how we can sample them. So we transform x1 and x2, and this just helps control the general behavior of all of this. And we transform them into these variables that we call tau, y, and z. So we define this tau here as x1 times x2. So longitudinal momentum fraction 1 times longitudinal momentum fraction 2. And we define that as here, this is just the partonic center of mass, or the partonic center of mass energy over the center of mass energy. Then we can do the same thing for y. Y, the reason it's called y is it looks an awful lot like rapidity, right? Except now we have something like x1 and x2. And then finally we have this z, and this z is just defined here as cosine of theta hat. And so what that means is we can rewrite this integral now for the massless case where we integrate over tau, so x1, x2, y, which is this here, and then z, and we can write everything out in terms of this integral here instead. So why have we done this? The reason is because when we want to go and sample these, so sample tau, y, and z, it means that they're functions that are behaved in a way that we can actually sample them. Otherwise, we'll end up having really kind of divergent behavior in some of these variables. And so this allows us to sample them. Okay, so as you can see already, phase space even for a 2-to-2 process can be calculated. And we have PDFs with these peaking behaviors. And so that means that we have these divergent cross sections. So what kind of cross sections do we have here? So this is QQ to QQ. This is if we're looking at differentially with respect to T hat. And it's written out like this here. And you can see that we already have divergences that will enter here. We can do the same thing for quark gluon to quark gluon. Again, differential in T hat. And again, you see that there are divergences that can enter into here. And for the case of gluon to QQ bar, again, differentially in T hat, we have divergences enter in here as well. And so what this means is that if we go back to this equation that we have here, we can get rid of those divergences and we can sample these functions in a little bit better behaved way. So what we do is we independently sample, and we use importance sampling for it, but we independently sample tau, y, and z. And then we carefully construct our oversampling function g of x for each of these variables, and we do it relatively carefully to maximize the efficiencies that we have for sampling this. If you don't use this oversampling, you'll be sampling forever, and it will take you forever to get anything out from any of this. So I'm going to go over this. I don't expect you to remember it all, but I do just want you to understand, really, even for the case of 2-to-2 sampling, how careful you need to be about doing this type of sampling. So we define these functions here. We have this oversampling function h of tau, which we write out in terms of these other functions, I1, I2, I3, and I4. I don't even list them here, but they're normalization terms that you have to calculate out numerically. Then we have this oversampling function for this y variable. Again, we have normalizations that enter into here. And then we have these c terms as well. I should say these c terms are terms that come in that are optimized for this. And then finally, for our last one, which is z, we again have normalization terms and then these optimization terms that enter in as well. All of these terms, right, they account for peaking behavior in resonances. And they also account for other types of peaking behaviors that you might have coming from the PDF. So for example, you can see here with this term right here, that this accounts for the peaking behavior in the resonance that you might be able to get out from this. Okay, so for HY, this one here, it's relatively flat, except this third term right here. And this comes from the peak at 0 from the PDFs, right? So this one handles the PDFs here. This one here handles the resonance behavior for the S channel. And then finally, the HZ, this handles the divergent cross-section behavior here, where you might need to have some sort of cutoff here. And you can see that enters here in terms of these terms of Z here. Okay, and then as I said, these I don't know why I have a right angle bracket there, but these I are these normalization terms, and these CI are these constants that can be optimized for whatever this is. So in the case of Pythia, the idea is that you select a 2-to-2 process. It can then numerically calculate out what it thinks these C values should be in terms of the optimization. There's a routine that does that, and it also calculates out what these normalization factors are as well. But already, again, just for 2-to-2, this ends up being really quite complicated. So I want to just pause here for a second, because it's very easy to say, oh, Monte Carlo event generators, 2-to-2 process, no problem. Really easy to just do that and integrate it out and sample from it. Turns out that when you actually go to implement it, it's a bit of a pain in the butt. Okay, so you can imagine that if you go to these higher order diagrams where you have additional legs, that it becomes even worse. Okay, so this is how we actually sample the kinematics for the 2-to-2 process. But we also need to be able to sample out what the color flow looks like as well. And this is really quite important, because if you remember, with our parton shower, we need to track what all the colors of all those other partons are. So if you think back to the tutorial from yesterday, where we were looking at the event record from Pythia, we had all these different colors for each of the partons, and we had to track where each one of them were going. And then at the end of that parton shower, we get these strings. If you change the ordering of those colors, if you change the way that those colors go, you will get very different topologies for those strings. You'll get very different hadronization topologies, and so you'll get very different events. So that means that we also need to be able to track these color flows as well. So let's look at a few examples of these color flows. So here, quark gluon to quark gluon. So here, for example, we can have something where we have our gluon coming in here. It takes something like blue anti-red. that blue comes through here, that green comes through here, and then we have our red going like this. We have another diagram where we can have this as the possibility for it as well. And then we also have, for example, these two diagrams where we can have different types of color flows. But now here, this is for the S channel, and this is for the U channel here. So 2 T channel, S channel, and U channel. So if we want to go and we want to calculate the color flow for this particular process, quark gluon to quark gluon, right? We have all of our individual matrix elements for T channel, S channel, U channel, but we also have a corresponding color flow for them as well. So how do we go about doing this? Well, the idea is that the total matrix element for this, right, the thing that we have entering into our cross section when we calculate that out, is the fact that we have these interference terms, right? So we have this interference term here. So we have matrix element 1. So let's say that that's T channel, and we have this one here. So let's say that's S channel. And then, of course, we have these interference terms here. So the idea in these types of generators is that we use this idea of the large color limit. And so when, again, you were looking at that Pythia tutorial, what you would see is that we didn't have things like red, blue, green, anti-red, anti-blue, anti-green assigned to each of the partons, but instead we had a number, and that number always increased, starting off at 101 and going up. So in the large color limit, instead of saying we have these 3 colors, we actually have these colors going to infinity. And it turns out that for events like this, this is a relatively good approximation. But the really important thing that comes out of this is that when you have this type of large color limit for this type of thing, if you take the interference terms and you divide them by the cross section for the total, that you end up with a proportionality where they're highly suppressed with the number of colors that you have. So in other words, you don't care about the color flow from the interference terms. You only care about the color flow from the terms that are just the diagram itself squared. That's the thing that you care about. So that means that you can write out your cross section like this. And then what you can do is you can factorize it. So you say, okay, for, let's say, whatever one of these, so S channel, T channel, whatever it is, or specifically whatever color flow you have. So this is a specific color flow, that's just going to be the total cross-section times the cross-section for that specific color flow divided by then this total cross-section here. And so what you can do is you can generate the kinematics, and you can generate them corresponding to the total matrix element that you have. And then what you can do is you can generate the color flow based off of this here. So basically, you're just choosing one of these color flows to set up. So to give an example, if we have this quark gluon to quark gluon going on here, what we do is we generate the kinematics for it, and then we choose one of these 4 possibilities for the color flow based off of this algorithm that we have right here. So this is the idea behind color flow. Now, it's interesting because in fine hex, right, we have this idea of these diagrams where we didn't have this ability to say what the 8 colors of the gluon were, right? Same thing here. So there's a thing called color flow representation for QCD, where basically with planar diagrams for color flow, you're able to show that you can recover the color factors for these types of cross sections. And this is something that you actually, if you really want, you can explore with in fine hex because it allows you in that formalism to fully calculate out what those color factors are. But that is a side note. Okay, so that's everything that I wanted to say about matrix elements and color flow for matrix elements. Before I move on, are there any questions from anybody about that? Okay, so I want to go back and take a look at these things here. So these are these integrated cross sections for the partonic cross sections. And we see that we have, for example, T hat entering in squared, S hat entering into the 4th. If we want to calculate these out with a computer, right, there's a finite representation for how you can hold a real number in a computer with this float format. It means that we have some finite precision by which we can calculate these things. So here is a relatively complicated matrix element here. This is the integrated matrix element for gluon-gluon going to then a D-wave state of quarkonium. So 3D1 in this case. So this is a specific quarkonium state. So for example, the Psi 3770. And you can write this thing out. And you can write it out in terms of T, S, and U. Here, I didn't put hats over everything. These are the partonic ones that we're talking about here. And you can see that we get some insane numbers on some of these things. So for example, we have mass to the 14th, we have s to the 7th, all the way down here, we have t to the 10th. So what we see here is we are adding a bunch of numbers that can end up being really, really big and subtracting a bunch of numbers that can be really, really big. And so when you do this numerically, if you take a really big number and you subtract a really big number, you don't necessarily have the precision to be able to calculate out what that is. So if you write your integrated cross-section out like this, you end up with a cross-section that actually makes absolutely no sense. Why am I giving you this specific example? So it turns out that LHCb wanted to measure production of this particular zirconium state. So we wanted to have a Monte Carlo implementation for it. Someone implemented it in terms of this cross-section here with no numerical conditioning whatsoever. We used these then to do Monte Carlo simulation. If I were to look at what the numerical precision of this thing is, I end up with some terrible, terrible things going on over here. So this is d sigma dt, and then this is t over m squared minus s. These are the two variables that I've chosen to look at here. And as you go out over here, where this cross-section actually really matters a lot, you start getting pretty much just random numbers, depending upon the state of your machine and the bits in it. And this is not something that you want to happen. And so what this means is that the cross-sections that we were getting out for this ended up being relatively meaningless. So this is something just to keep in mind, that if you don't numerically condition your cross-sections, you can end up with something that really gives you something nonsensical. So the question is, how would you actually approach a problem like this? You'd basically try to factorize it in such a way that you minimize these factors on these Mandelson variables. And if you use Mathematica, it's really quite nice because in the simplify routine for Mathematica, you can actually specify the metric that you want to simplify over. And so you can tell it the metric actually is making sure that these are relatively small powers in terms of how it simplifies things. And so this is actually exactly what I did when I needed to go fix this, is I took this and then I ran it through Mathematica with this simplify function where I defined this specific metric, and then it was able to give me a conditioned form, which in retrospect I probably should have showed here as well. It's also just as long, but it no longer suffers from numerical precision issues. Okay, good. Questions on this at all? So now I want to talk about, well, what happens if you want to do some sort of cross-section that isn't just 2 to 2? Let's say you want to go to cross-section 2 to 3, 2 to 4, 2 to 5. Or let's say that you actually want to include some sort of loops in your cross-section. So you want to go to next to leading order in terms of these virtual contributions. It's important that we think about this in terms of Monte Carlo event generation, that we think of it in terms of order, not just order by itself, so the number of alpha s that enter into the diagram, but rather in terms of whether number of alpha s that we have in terms of the number of legs that we have, and then in terms of the number of loops that we have. So this is a little diagram that I stole from, I think, a presentation by Peter Scans, where we have these legs on the x-axis here, and we have the loops here. And so what do I mean by a leg? By a leg, I mean a real emission from a diagram. By a loop, I mean a loop in that diagram. And so if we're sitting down here at Born level, that means that we have no loops and we have the minimum number of legs possible. And then we can go out in terms of legs without increasing the number of loops. So for example, if I had something like a 2 to 2 process, this could then become a 2 to 3, 2 to 4, 2 to 5, etc. Right? That's the number of additional legs that we get on there. Then in terms of loops, this is particularly important, for example, in the case of Higgs diagrams. The higher the loops that you go, then you also get these contributions as well. You see here, this 0 here indicates these kind of superscripts here indicate the order that we're calculating this whole thing out. So in terms of what this looks like, there's this important thing here, x plus 2 at leading order, that this is actually really quite important for many LHC processes because you need these additional things. So here we have 2 additional jets. So this would be something like a 2 to 4 process instead of a 2 to 2 process. Or let's say we're doing something like QQ bar going to Z. Then here, this would just be the Z being produced. Here it'd be the Z being produced with 2 jets. Okay. So then we have, for example, x at next to leading order. So if we're really saying next to leading order, that means that we include with just no additional legs, our loop calculation. And then when we have one additional leg, we include this as well. The important thing for something like this is that when we do this, that our observable, when we are at the Born calculation, this is truly next to leading order, but when we go to this additional leg that we have, that leg really is only correct at leading order, right? It's only being calculated at leading order. And so you can see playing this game, right? If you keep on going up in terms of the number of legs that you have. So here, if this was just a z, and this is z plus jets now, right? So if I'm calculating x plus 1 at next to leading order, so this is something like z plus jets here, then what we see here is that in terms of these observables here, that the x plus 2 jet observables are, again, only correct at leading order. And so let's say that you really wanted to go at next to leading order, which is something that we oftentimes now need to do. That means you need to calculate a whole bunch of stuff. It means you need to calculate just Born level, right? Then one leg, two leg, then one leg with virtual correction, then 0 legs with virtual corrections, sorry, one loop here, and then 2 loops at 0 legs as well. And so again, here, the observables, when we go at x plus 2, only correct at leading order. So the reason that I'm going over this is because when you have a generator, it's very important to understand where that generator will be generating at next to leading order, where it will be generating at leading order, where it will be generating at next to leading order. So if you take a Powheg box process that's at next to leading order, that's next to leading order when you're looking at whatever that process is. When you want to throw on another jet to it, that is only going to be then at leading order, if you're looking at that specific exclusive variable. So this is something to keep in mind when you're looking at these types of predictions. So significant work has gone into filling out this schematic in terms of what this is. This is, again, a plot that I stole from Peter Scans, so it's a little bit old, although it hasn't moved a huge amount since then, which is state-of-the-art as of 2019. So what we have here is number of final state particles, number of loops here. And this is for a specific process. I think in this case, this is Drell-Yan. And so you can see that we can go out all the way in terms of these legs, whether it's done for some processes or not. Sorry, this is for a number of processes, not all processes, but kind of the gold standard usually is Drell-Yan. And so you can see that we've gone all the way up to loops here, for example, of 3 loops, but only at this 0 legs here. And then you can go out and you can see that we only have this in terms of our triangle. And it depends upon the event generator or the way that you're simulating this. And so for the general purpose event generators, so Sherpa, Herwig, and Pythia, Sherpa has an automated way to go out to as many legs as you want. In practice, if you go out beyond 8, the phase space integration really doesn't work particularly well. And it can go up to 1 loop as well. Same thing for Herwig. Pythia itself doesn't do matrix elements at these higher orders. It can usually go up to 2 or 3 in terms of the number of legs. It's not automated. And this is why people oftentimes use MadGraph in addition to Pythia. MadGraph itself can do 1 loop plus then whatever n that you need to have here. Okay, so number of tools providing this is relatively high in terms of automation. And I went over some of them. So for example, with Sherpa, this is done with Comex. With Herwig, this is done with Matchbox. And then with MadGraph, this is done with AMC at NLO. And so in MadGraph 5, this is now fully integrated with AMC at NLO. So this is how it's done. Okay, so this is loops and legs. All right, now we've got the matrix element. We know how to calculate out the color flow. We can do it for 2 to 2 explicitly. If we want to go to higher orders, we have a rough idea of how that works. But we're still missing additional higher orders within it. So for example, if we have Z plus 1 jet, that's going to give us a quark. But there's or a gluon, right? There's a possibility that we could have additional jets as well that aren't covered by that matrix element. And so we want to be able to make sure that we include those. So let's take an example where we have QQ bar going to Z. So this is our diagram that we have going on here. And if we do it at leading order, so it's a 2 to 1 process, that means that in our factorization that we have, right, we have no transverse momentum in those PDFs as we factorize things out. That means that if we were to calculate this out, that at this lowest order, we would have a finite cross-section. and the PT of that Z would be 0, because there's nothing for it to recoil against, right? It's going to have 0 PT. This is not really what we want, particularly when we go to measure, for example, the W mass, where the PT spectrum is oftentimes how we access that. Well, if your PT spectrum is just a delta function at 0, you're not going to get anything out, right? So that means you'd like to do a little bit better. So you could say, well, okay, I add on my additional jet. So I have this real emission here, yeah? So this now gives me some sort of PT spectrum, because now I have a 2-to-2 process. And then you can say, well, I have a virtual loop as well, and then that can give you some sort of contribution as well. In this case, it could give you, for example, something like a negative contribution. So this actually starts to introduce some problems with generating the Monte Carlo, because typically you like to work with real weights when you add these things together, but now you can start to get negative weights as well. Now there are a number of different ways that you can calculate these things out, and you can force yourself to have positive weights. So there are various techniques that allow you to do this, which in general is quite nice, but sometimes they're quite cumbersome and they're not always easy to implement. And so sometimes you get negative weights as well for many of these tools. So this is something that you have to be careful about. We typically think of these things as these counterbalance terms. And what it means is that when you're plotting out observables, or you have events generated with positive weights or negative weights, that you don't have those types of things crossing boundaries, so you have these large fluctuations in your observable. Okay, in terms of these types of things, if we want to look at high mass searches, so for example, let's say we want to do some sort of SUSY search or some sort of new physics search at really kind of high mass, you can imagine that these high PT tails are really quite critical. And so that means you want to go to as many number of legs as you can, but you have to be really careful about how you go about doing it. Okay, so this is matrix elements. In terms of these contributions that we have, this is the Higgs mass. This is the cross-section for the Higgs inclusive. You can see how these things scale. Leading order is given in green. Next to leading order is given in blue. Next to leading order is given in red. For most of these processes that we have, the nice thing that we see is that by next to leading order, the results typically begin to converge. What I mean by that is that the difference between leading order and next to leading order is bigger than the difference between next to leading order and next to leading order. So this is a good behavior. That means that even with next to leading order, because we see this convergence behavior, the things that we're getting out aren't totally crazy, but we still might want to go with higher orders as well. And in general, this works relatively well for inclusive cross-sections. But again, looking at that loops and legs diagram, we really have to be careful for these differential cross-sections, because if you're measuring something exclusively, where you're requiring a certain number of jets or something like this, then you'll start to run into problems. Even if you're looking at something like the PT of the Z, you'll run into problems. Okay, so we have this cross-section. It's calculated out at next to leading order, however many legs we want. Great. But again, it still doesn't give us the full picture. Here we have just a tree-level diagram, so QQ bar going to QQ bar. We really want to be able to then get out from this our hadrons. And this is where the parton shower comes into play. So conceptually, the idea is that you would apply each of these things here. So you could say, well, okay, I'm going to really calculate out this matrix element, but we've seen that this is really kind of hard to do. So if I wanted to look at the phase space for something like this, for a matrix element, it would be totally crazy, and I probably wouldn't be able to do it. Now, if I wanted to do it, I would need to use Monte Carlo integration. But instead, what I can do is I can say, well, I actually do this perturbatively. And I do it iteratively for each of these things here. And as I go from this kind of high scale here to this low scale, I decide at some point this perturbative iterative process doesn't work anymore, because I've gotten to the point where my alpha S is too high and it no longer converges at all. And at that point, then we need to have some sort of model enter in that's a phenomenological model for hadronization. Okay, and that is what this is here, this model that we have taking these partons to hadronization. Of course, we have the problem on the other side that we need to be able to go from this hard process here to the scale of which we actually extract the partons from the proton as well. This here we call final state radiation. this here we call initial state radiation. Both of these are part of what we call the parton shower, where we do this iterative procedure using these perturbative splitting kernels for these things. Okay, so let's take a step back and actually motivate how this goes and how we can do this. So we can think of a process where we have E plus E minus going to Q bar. And we can think, well, what happens if we have an additional gluon? So we can say, well, let's define what our coordinates for this are. So in this case, we have E plus E minus going to Q bar, and we're throwing in an extra gluon. We can say, okay, let's go into the center of mass frame for the Q bar system. We define this angle theta that the gluon makes between this. And so then we can say that this gluon has this momentum fraction Z, or energy fraction Z, which is the energy of the gluon over the energy of, for example, the quark. So then we can say we have two diagrams for this. We have one where this gluon is coming off of this quark, and we can have another diagram where this gluon is coming off of this antiquark. And what we can do is we can write down the differential cross-section for this. And what's really important is that this differential cross-section in terms of Z, so this energy fraction that this gluon has, it turns out that we can write it as the cross-section, so the inclusive cross-section that we have, times then these terms that we have here. So this theta is just this angle of the gluon and the quark, between the gluon and the quark. This NC is just the number of colors that we have. Those are the two things that we have that enter into this, and then, of course, alpha S as well. So this is really quite nice. And I should note that this is an approximation. This is an approximation when this gluon here is either collinear with the quark or relatively soft. And so what we can do is we can factorize this into a general form of splitting kernels. And so we can say this differential cross-section is going to be equal to this cross-section, the total cross-section, times every type of possible splitting that I have like this, where this pi is encoded by these terms that we have here, where we have this theta and Z. And again, this is an approximation that we have, but it's actually really quite close. So we lose some terms here, but in general, it's a relatively good approximation. And this is the idea behind the parton shower, is that we're able to take these splitting kernels. So in other words, quark emitting a gluon, or something like this, and we're able to figure out what each of these is using the rules of QCD. And then we can take our cross-section, our inclusive cross-section, and we can get a differential cross-section out from this. So something that's important to note here is that this thing diverges when this becomes completely collinear. So when theta becomes 0, this thing diverges. So theta or pi, so you see that here. 0 or pi, you see that here in this term. Or when we have something that's infrared. So when this Z goes to 0. So in other words, this gluon energy becomes really quite small. And in that case, this gives us a divergent term here. So the way that we set this up in terms of our sampling, we have to be very careful because we have these divergences enter. Okay, so now that we have this idea of these splitting kernels, we want to be able to iteratively produce, basically, a quark emitting a gluon, or a gluon emitting two gluons, or a gluon splitting into a quark and an antiquark. This is effectively just DGLAP evolution. It's a Markov chain formulation of DGLAP evolution. So how do we algorithmically go about and calculate that? Well, the idea is that we have this equation here. This equation here tells us here what our probability from transitioning from one energy scale to another energy scale is. So the way that we go about doing this, and you see that this Pj enters in here, these are the splitting kernels from this previous slide here. That's this here, which corresponds to this right here. Okay, so how do we go about doing this? We pick a uniform random number R. Then what we do is we solve for this right here, for whatever that R is. And specifically, we solve it for this Q squared. So in other words, this is telling us that we are going from this higher energy scale Q squared to this lower energy here of small q squared. So in other words, what is the probability that I'm going to have this quark emit a gluon? So what we do is we solve for this q squared, this lower energy scale. And we say, in that energy range or in that scale range, whatever we're doing here, we're saying that we have no emission whatsoever. And then what we say is we say, okay, we generate an emission at that new Q² scale. So we generate an emission. In this case, we emit a gluon, for example. And then we go back to the start. So our new scale now is this small Q², and then we want to generate another Q². And in this way, we iteratively go along this process, and we evolve to this lower Q² scale. Once that Q becomes small enough, we terminate this entire shower. So this whole thing stops because we've entered a regime where these splitting kernels no longer are valid anymore. Okay, this is what we just call the veto algorithm. This is what I skipped in last lecture. If you want to go into more detail specifically about the derivation of the veto algorithm, we can do that. It is in the slides from yesterday. But for now, just take this as a form of veto algorithm. The idea being that effectively what you do is you look at a non-emission probability. You then get the scale at which that non-emission probability happens. And then you generate an emission at that scale, which is really kind of a cool way to go about doing this. And this is how a parton shower works in general, is with this algorithm here. Now, of course, parton showers by this point have gotten really quite advanced and quite complicated. And there's been a lot of work to make sure that parton showers and resummation, even though they're coming at it from very different views, end up giving you formally the same result. And so there's a huge amount of work that's gone on top of this. This is just an introduction to how a parton shower is done. Now, this is here a time-like parton shower. So specifically, this is our final state radiation, where we're taking a quark and we're having it irradiate a gluon, or a gluon having it split into QQ bar, whatever it is. This is when we're evolving on this diagram here to the right. So this is our time-like shower here. We also need to do something here. And this is our space-like shower, where we're going from our hard process back to these protons here. So effectively, we need to do this process backwards. The nice thing about it, it gets a little bit more complicated. The nice thing about it is that these splitting kernels still enter into this equation here for this, we call this whole thing the Sudakov factor. When we're calculating this out, these same splitting functions enter into it. The only difference that we have is we now have to scale it by the ratio of the PDFs for whatever that parton might be. So that's what is being given here. This K is the flavor of whatever the parton is. This is the scale of the PDF, and then this is the momentum fraction that it's carrying. So again, this X here, this initial X, when we enter into this is just given by the hard scatter. And then what we do is we evolve from our low X to our high X, and from high Q to low Q. And again, this whole thing, the space-like parton shower, which gives us initial state radiation, it is, just to be clear, same as the time-like shower, but now we're going basically backwards in our Q. So instead of going from high Q to low Q, in terms of our X. So we're still going from high Q to low Q, but we go from our low X to high X. And the way that we do that is by the incorporation of the PDFs here. So this is kind of the key ingredient in something like a space-like parton shower. Okay, so I want to go into a little bit more detail about the components that make a parton shower, specifically these splitting kernels. So I said these are the same splitting kernels as for the DGLAP evolution. And so that means that we can make sure that we calculate them out perturbatively. And so I'm going to just go through them here in terms of proportionality. So I'm not giving the full splitting kernels, but rather just the proportionality for it. So we have in just standard QCD, we have gluon to gluon gluon, quark to quark gluon, gluon to quark quark, QQ bar. If we want to have other things enter into this, for example, if we want to have photons, or if we want to have W, or we want to have Z enter into this, so no longer just a QCD parton shower, it starts to complicate things a lot more. The photon, not so much. W and Z, a fair bit more. Okay, so for the case of gluon-gluon, we have a gluon, it splits into two gluons. We write it out in terms of these factors of Z here. Notice that we've integrated for this over our other variable that we have, which is theta. Typically in parton showers, this is how it's done in terms of the sampling. Here, for the quark going to the quark plus gluon, so we're just emitting a gluon here, Again, just in terms of Z, this factor of mu here comes in as a mass factor. So this, without a mu, that is just if this is a massless quark. If we include the mass of the quark, we have this correction term here of mu. In parton showers, typically what we do is we'll sample something like this in the massless case, and then we apply a correction to the sampling that we've done. And then finally, we have gluon going to QQ bar, where we have z squared, 1 minus z squared, plus mu squared. Again, we have this mass term entering for the mass of the quarks. Something that's really interesting to look at this is if we have something like gluon going to gluon-gluon, this is a symmetric function in terms of z, as we expected it should be. This here is no longer a symmetric function anymore because we have a quark and a gluon. This is a symmetric function again in terms of z. So this is something to keep in mind when we try to go about sampling these things. Okay, so if we have these splitting kernels, so is there a question? Okay. Or a comment, because it can be a comment as well. Okay, so we've got this parton shower. So we have hard matrix element, parton shower. We get to the point where we have a whole bunch of partons in the final state. Then we apply hadronization, which, again, in this lecture, we're not talking about. We'll talk about it in the next lecture. But when we get to an experiment, of course, we want to be able to take that experimental result and compare it to theory results. And ideally, we'd be able to compare it to theory results no matter how they're calculated. So if we calculate a theory result with a fixed order calculation, so without any types of parton showers on top, or whether we've included parton showers as well. And so that means that we want to be able to unfold from to this initial hard partons that we have from the final state particles. And of course, this is where jets enter into all of this, and jet finding algorithms as well. So if we think about the problem that we have here, it's nice to be able to define a few things. So the first is collinear safety, and I think you've run into this already in lecture, but it's good to just give it again, which is collinear safety is when you have an emission from one of these quarks, and it changes nothing in terms of the observable that you get out. So we're thinking of some sort of observable. Cross-section is a function of whatever. It can be any type of observable, but is it an observable? So if you have basically another emission, which is along the direction of whatever it was coming from, this means that we have collinear safety. Infrared safety is when we have an emission that's very soft, and it changes nothing. Now, it's really important to keep in mind here, collinear safety, infrared safety. In the literature, it's very rigorously defined. When we look at observables, we can think of it in a very rigorous fashion. But from a practical point of view, you have varying degrees of infrared safety and collinear safety. So you can imagine an observable where if you have a semi-hard emission, nothing changes. But you can imagine another observable where if you have a semi-hard emission, something does change. So while there are rigorous definitions for this, it's actually interesting to think about it in terms of kind of a gray area instead of just black and white. Okay, so why is this important? Well, this is important is because if we have something that is collinear safe and infrared safe, then it really should be insensitive to non-perturbative effects. It means that basically we should end up with something where we don't really care what's going on with that hadronization at all. And that is why we use jets at the LHC, right? Is because we want to be able to make ourselves as insensitive to any type of hadronization uncertainty that we might possibly have, because we don't want to deal with these non-perturbative effects. And the other thing, as I said, is that you want this really to be applicable to both the parton and the hadron level. So in terms of this unfolding that we can do, we want it to be applicable to both the parton and the hadron level. So at the LHC, again, the way that we do this typically is with this sequential clustering algorithm. And this is the algorithm that we have in terms of this sequential method. We define this distance metric, this Dij, for 2 partons or 2 hadrons or 2 particles, whatever it might be. You can apply it at any point in this chain of the Monte Carlo event generator or on data, right? And then what you do is you calculate out what this distance is, and it's in terms of this minimum PT of one versus the other of these 2 particles, and then this angular separation between the 2 of them. And then we also define this distance relationship with respect to the beam or the z-axis as well. And so the way this algorithm works is you select the minimum d. If it's between 2 particles, you combine those 2 particles together. If it's with the beam, you say, voila, this is a jet. I'm removing it from the clustering. And then finally, if you have no particles otherwise that haven't been clustered, that have been removed, then you go back to 1 and you keep on doing this over and over. And so this is why is this sequential clustering, is because you do this clustering per algorithm step, where for each of these you calculate this minimum distance, this minimum Dij for each of these. Now, this algorithm, the reason that I give this algorithm right after giving the parton shower is because hopefully you see a connection between the two, right? If we think about the parton shower, we have effectively a sequential unclustering where we have 1 going to 2, et cetera, et cetera, et cetera, right? And so this is doing the reverse of what we're doing with the parton shower. And that's why we have these jet finding algorithms built the way that we do. And of course, a lot of work has gone into A, implementing these, and B, making sure that they truly are infrared safe and collinear safe as well. Okay, so this type of sequential clustering, these are some examples of it. So this is the Cambridge-Aachen routine here, where P is equal to 0. This is where P is equal to 1, so this is the KT clustering. And then this is anti-KT, where this P factor is -1. And you can see why for many LHC applications, for many measurements up to this point, this anti-KT algorithm is used. It's because you end up with these kind of nice round jets in terms of this rapidity phi space that we have. In terms of this, we can think of Cambridge-Aachen. It really only considers geometry. KT and anti-KT also consider momentum. And then, as I said, this anti-KT includes these types of circular jets in terms of this R variable that we have. So this is a nice kind of thing to take out. Now, depending on the type of physics you're trying to do, you might choose one of these over another one. And we'll actually see an application for using, for example, the Cambridge-Aachen algorithm as well. So what happens if we have a really boosted process? So in other words, we end up something where we have a really, really hard scale that's happening, and the observable that we're looking at is on a relatively low scale. So let's say we have something like a very, very boosted W being produced, and we want to look at the decay of the W, or a really, really boosted Higgs being produced, and we want to look at the decay of that Higgs. What would initially have given us 2 jets with our standard jet clustering algorithm now are going to be right on top of each other. So we need to be able to do something about this, where we separate out, we tease out those 2 kind of subjets that we have. So this anti-KT, it produces a single jet, and so we use jet substructure to figure out really what the process that we had is. One of the main ones out there is soft drop, but there are quite a few techniques, and recently there have been even more techniques that have come out, but I'm going to go over the soft drop technique here so you have an idea. Now, this soft drop technique is going to connect back up to the parton shower, because with the parton shower, we're going from our hard process to our kind of our final state. With our jet clustering, we're connecting those 2 up. Now what we want to be able to do is we want to be able to go 1 step back, basically in our parton shower. We want to be able to look at what does that splitting actually look like. So this is what soft drop does, is you create these kind of trees. So we have this jet here, and in this case, this jet is an anti-KT jet, and it is a fat anti-KT jet. So let's say our radius that we're setting up for our jet is 0.5. With a fat one, maybe we use something like 1 instead. So we have this fat jet, and we're trying to get some sort of substructure for it. So this is our jet, J0 right here. Then what we do is we build a Cambridge-Aachen tree for that fat jet. In other words, if we were to take all of those partons, how would they cluster together? Or all of those particles, how would they cluster to give us this one jet here? The reason we use it with Cambridge-Aachen is because Cambridge-Aachen doesn't depend upon the momentum at all. It is just an angular clustering. So we think of this only as an angular clustering. And so this is what this Cambridge-Aachen tree might look like, for example, where we have all of these subjets. So we have all of these particles that went into this jet. And then as we were to build this jet here, we combine, for example, these 2 together to give this one here. We combine these 2 to give this one here. We combine these 2 to give this one here, et cetera, right? Okay, so what we then do is we split this jet J0 into 2 jets, J1 and J2, from this Cambridge-Aachen tree. And then what we do is we choose J1 or J2, or we stop soft drop if the soft drop condition is met. Specifically, this is the soft drop condition here, where this is PT of jet 1, jet 2. This then is the delta R between them. This is some R parameter that we have, and then this beta is a parameter for the soft drop as well. However, if that condition isn't fulfilled, then what we do is we then say, okay, I take the larger in terms of PT of those two subjets, and then I go back to 3 and I do this whole process over again. What is this telling us? Effectively, what it is doing is it's removing all of these soft emissions that we might have in a fashion that is very similar to the way that the parton generates those soft emissions in the first place. And so the idea is that what you can do is you can go backwards until you get to kind of the hardest splitting that you have of that jet. So the cool thing about this is that you can actually use soft drop to directly access these average massless splittings. So if we go back to this slide here, we have all these splitting kernels. We would like to experimentally validate that these splitting kernels are what we think they are. Soft drop effectively allows us to go back and measure these splitting kernels. Now, there are a lot of caveats to it, but that is effectively what it allows us to access. Okay, so what does that look like? Well, it turns out that when we have something like this, we can't determine typically whether it's a gluon going to gluon-gluon, or a quark going to a quark plus a gluon, or a gluon going to quark plus an anti-quark, if we're working with just light quark flavors. So that means that we need a mass averaged, or an average splitting kernel between these three things for massless splittings. And that's what we get here. And so then what you can go do is you can go and you can look at data, and you can build your fat jets, and you can then take a look at soft drop, and then from soft drop, you can calculate out this quantity here. And this then gives you access to this hardest 1 to 2 splitting, and this is what it looks like in data. So this is CMS open data. And you see here, the points are these black points given here. And it's taken from this paper if you want to take a look at more details about it. And then you can see that it's compared to what Pythia gives you, what Herwig gives you, and what Sherpa gives you. But specifically, this line here is what this average splitting should look like. So you're able to directly access what this splitting should look like, which is really quite cool. Now, ideally, what you'd like to be able to do is you'd like to be able to look at these different ones. So you'd like to be able to set these up so you could look at these different ones. If you use flavor tagging, you can do exactly that, because you can determine which side of the jet has the flavor tag and which side of the jet is the gluon, for example, or which side of the jet is the quark and which side of the jet is the anti-quark. So you're also able to experimentally measure it that way too. Okay, so now I want to go back to parton showers and go back to these splittings. There are a bunch of different parton showers out there, and I'm going to talk about the LEP era ones first, where we kind of had these 1 to 2 splittings in terms of both Pythia and Herwig. And these are the types of splittings in terms of the formalism that I gave you here. This is how it's thought about. That we have these kind of 1 to 2 splittings. There's also this dipole formalism, where instead of just thinking of a quark by itself or a gluon by itself, you think of these things as actually these color dipoles that you have. And in that case, you have a 2 to 3 emission. So for example, you have this quark anti-quark, and then you can have radiation coming off of this. And so this is the Ariadne parton shower. At this point in time, most parton showers are somehow have gone beyond this, but they're more in the kind of formalism of a dipole parton shower. And the idea is that you have this gluon being emitted, or you have two gluons being emitted, or whatever you might be having, but you think of it as coming from this system instead of just from a single quark or a gluon by itself. So again, these kind of newer parton showers, whether it's Vintia, Dyer, which no longer really is being developed, but other ones as well, whether it's something like pan scales or something like this, are motivated from kind of this dipole-like type of generation that we have. The other thing that I want to talk about that's important is the ordering of these parton showers. So if you remember, when we were going through this veto algorithm for the parton shower, we had this scale Q squared, and I was talking about it kind of like an energy, right? But we need to kind of precisely define what that scale is. So in the LEP era, Pythia defined that scale as this mass squared of the system. And if you look at something like rapidity here, and you look at PT here, that effectively is corresponding to evolve in your kind of parton shower inwards along these lines. And so for the case of Herwig, it used this angular ordering where it was energy squared, theta squared, where there's this angle theta that's entering, and that effectively corresponds to going outwards like this. And finally, Ariadne used this scale as PT squared, and that kind of corresponds to going downwards on this in terms of the types of the type of ordering variable that you have here. So it turns out that each of these, they was chosen for a very specific reason, because they allowed certain things to be done better than other things here. So for example, in this, you cover your phase space really quite nicely. Here, your hardness really isn't ordered so much, so there are gaps in your phase space. And here you actually end up with something that's quite nice, but then calculating your ISR ends up being a little bit more messy. It turns out that in modern parton showers, this PT ordering is used almost all the time. So you'll see here that Ariadne was kind of ahead of its time, because we now more often than not will use this kind of dipole motivation, and we'll also use this PT ordering as well. So specifically in Pythia, this PT ordering is used in Pythia 8. Okay, so that brings me to the end. I want to just give a brief summary then of all of this. So factorization theorem, of course, it's crucial to be able to do any of this, because otherwise we're not able to calculate out these cross sections where we actually have beams. So we factorize it into the partonic one that we can sample, and then these PDFs. Sampling these matrix elements in phase space, it really can be quite tricky. So it is really not a trivial thing, even when you're just doing tree level diagrams. You definitely need to be very careful about numerical precision issues. This has come up any number of times for any number of event generators. Another interesting kind of current example of this is that for the PanScales team, they're really trying to validate kind of the accuracy of these parton showers. So they need very, very good numerical precision. And they have spent so much time working on getting that numerical precision. It's really quite crazy. Some of the tricks that they have to do for this numerical precision is totally bonkers. If you read the code, you'll have absolutely no idea why they're doing it that way. It's because of numerical precision issues. Okay, then we talked about these kind of terms that enter into these matrix elements. So both real and virtual contributions, where you can have negative virtual contributions. So you have these kind of counterbalances that enter into this, where you have to be careful about looking at exclusive variables in terms of real emissions, because you might not necessarily have your virtual contribution entering into that. There's been significant progress on this kind of automated work for this, but for where there isn't something that goes out quite as high as you want, the parton shower can then fill in the gap. And there are ways to actually go and try to validate these types of parton showers in data as well. So in the end, there's really quite some choice with corresponding pitfalls as well about how you construct these parton showers, whether you use a dipole formalism or not, what ordering variable you use and whatnot. They're all really quite important to consider, but it really depends on what you're trying to do. So that's pretty much all of the advice that I have on parton showers plus matrix elements. Questions? Yeah. Yeah. Okay. So you will see, right. So your question is, let's start with the easier one here, right? That we have this totally nasty thing here. How do we do this inversion? You use simpler functions. You sample in a way that you know what those simple functions are, but you're actually getting the real thing out. And then you can invert for those simpler functions. So we are going to have a tutorial on that on Wednesday, where you'll see how that's done. But really, it is quite the implementation. The devil is in the detail for sure. Yeah, 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 yeah. Yeah, you could. I'm not the person to be. Yeah, okay, so I should say, if you want to read about these in gory detail, look at the Pythia 6 manual. They're given in full form and how all these things are calculated out. To answer your question, I'm not the person to be asking that question. This particular parameterization for all of this came from Torbjorn Sjöstrand, and he came up with it, right? In terms of the way that you do it with these automated matrix element generators, and you have this really kind of large scale phase space generation, there are general rules that are applicable here as well that you can take to larger number of things that are entering into this. So for example, you'll have these kind of resonance terms entering into the oversampling, and you can do this in an automated fashion. And then you'll have just these PDF terms that enter here. That actually luckily doesn't scale. But in general, you have to be really kind of clever about it. But there are automated ways to do it. But that's pretty much all I can tell you. That's where my knowledge ends. Yeah. 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 Yes.
This is some simple process with jets added to it as you go to the right.
As you go to the right, more jets. Yep. As you go up, more loops. This is from 2019 as well, so it has changed. Yeah. And I also didn't make this plot, but yes.
So this is
Okay. So at this point, you probably, I don't know. You could take Sherpa, and you could say, I want 25 jets. And it would calculate it, I think, and then it would die when it tries to do the phase-space integration for it. I don't know how high you can push Sherpa or MadGraph without them dying. Some of you might have better ideas. Right. So in principle, right, it's automated, so it can be done. It can do it, right? But it's getting to a point where the phase-space integration is so large that it just can't do anything with it. Because it has to, so back to your question here, right? How do you actually know how do you set up those oversamples? When you have this automated process, effectively what you do is you start off with some sort of integration grid. You do that integration grid, you build up your kind of multi-channel sampling from that. And then as you go along, you refine that multi-channel sampling, knowing ahead of time where your resonants are kind of sitting, right? If you go to a really high order phase space, that becomes a really hard problem to do. And so that integration really starts to fail. Yeah. So if I had to make a guess, then I would say that you can go as high order here as Vegas can handle, because effectively these phase-space samplers can do better than Vegas for these specialized kind of setups, but not a huge amount, I don't think. So yeah.
Are there any efforts to integrate GPUs?
Yeah, okay, we can, so the thing about GPUs, right, is that you want to have a bunch of things happening in operation at the same time, right? So Monte Carlo generators are sequential in the random number sequences, yeah? So in the current formalism that we have for Monte Carlo event generators, it is not conducive to a GPU because you can't run all these things all at once, right? The thing from before depends upon the thing that just happened, right? So a GPU is not particularly well suited for it. Now, that's not to say that people aren't trying. So you can try to take some of these algorithms and write them in a way that they can be implemented on a GPU. Relatively tricky. There are other things that you can do as well. I know that there is a very, very rudimentary parton shower out there that can run on GPUs, but the way that it works is not what I would consider to be a full rewriting of the parton shower algorithm for GPUs, but rather some tricks. But it might be in the end that we just do a bunch of tricks, right? This is not to degrade tricks. Tricks allow us to get all this stuff done. So yeah. So random number generation for the tutorial.